I'll turn the mic over to Aman.
All right, thank you everyone for joining. Well, last year, an AI agent basically meant a chatbot, right? So you ask a question and it gives you answers. Well, not anymore. Agents are out there shipping code, opening pull requests, managing emails while people just sleep, right? But if you look very closely, almost every agent, even the autonomous ones, share a simple habit, right? So they simply wait. Now, a chatbot typically waits for humans to ask it questions, but even the autonomous ones often wake up periodically and check if there's any other pending work to do. So that is basically just polling, right? So I think the autonomy part is being addressed, but the part that is still kind of clumsy is the sensing part, right? So how do we know the moment when the agent should be taking an action? So that's what we are about to talk here. So I'm Aman, and I work on Drasi, which is a open source CNCF project. And sensing change and reacting to it is the whole thing that we do. So today I will show you how to build agents that react to data changes without polling. So let's start with an ambient agent, right? So what is an ambient agent? Well, it is one that runs quietly in the background and it acts when something changes. So nobody has to really prompt to the agent to do something. But here's the catch. Reacting to these changes are only as good as the ability for the agent to sense these changes when they're happening, right? And the changes that matter most are often really hard for a polling agent to easily detect. So sometimes the important thing, for example, isn't that something has changed, but rather that something that should have changed but did not. So let us look at this example when an order was placed, right? And it goes into processing state, but then it just sits there. It's just stuck for 15 minutes and no movement. So no errors, no crashes that you could just simply poll for or process an event, right? So the signal here is basically the absence of a change. Now, with polling, you must keep periodically checking whether something has changed, whether the order has moved yet, is it still stuck in processing, and you must periodically check that and then keep track of time and do the math to basically evaluate this condition, whether the order is stuck for 15 minutes or not. Now, what if the agent could simply be told, hey, this order has been stuck for more than 15 minutes, and you can just simply escalate to the appropriate ops team? And what about the opposite problem, right? So sometimes the data does change, but it is too fast for an agent to keep up. So let's say the agent is monitoring credit card usage. Now, normal charges should be at least a few seconds apart, right? But what if there's a burst of 5 charges within a single second? Now, the fraud signal here is not a single transaction because it just looks normal, but the fraud signal here is the gap between the transaction collapsing. So good luck catching that with polling because you would have to basically poll at sub-second intervals forever. Because if you stop polling, by the time your next check runs, the burst is over and the money is simply gone. So what we do need to do here is to compare each single change or each single charge that happens in the card as soon as it happens with the one that happened just before it, right? So one scenario was where changes were too slow to bother polling for that, and the other scenario was where changes are happening too fast to even detect using polling, right? So what we need here is something that watches these data changes for us and taps the agent on the shoulder whenever something actually matters. So that's Drasi, a change processing engine, and it's completely open source, part of the Cloud Native Computing Foundation, and it has three simple pieces. The first is sources that helps Drasi connect to your existing systems. Now, think Postgres, Cosmos DB, Kubernetes clusters, message queues, APIs, whatever. So Drasi, with these sources, is able to connect your data systems wherever your data lives today. You don't need a central data lake or data migration project. The second piece is called continuous queries, and these are simply graph queries that can span all these systems at once. And these can describe the logic that you really care about without writing any custom code. But here's the twist. Now, a normal database query is basically a snapshot in time, right? So you run a database query like a SQL query, and you get the results based on how the data looked at that point in time. Continuous queries in Drasi watches the change feed of your source systems, and with that, it basically keeps an incremental view of all the data and keeps your result set always current. And when this result set changes, Drasi is able to emit delta notifications informing what was added, what was updated, what was deleted, with the context of how things look before and after the change. So, sure, we got an honest result set and a stream of exactly what is changing, but what can we do with that? Well, that's where the final piece comes in. It is called reactions, and reactions invoke external systems when these query results change. You could post to Slack, you could kick off a workflow, update a vector store, or wake up an AI agent, right? And these are some of the integrations that we have in place, and we are always building new. So how do we build a LangChain agent with Drasi, right? How does Drasi connect to a LangChain agent? Well, Drasi also has an MCP reaction. Now, instead of posting to Slack or calling a workflow, this reaction simply exposes Drasi queries over MCP, a protocol that your agents already speak. And on the agent side, we just do one simple pip install command, and it gives us a new tool, which we wire up like this. And that's it. The agent then gets three new abilities, right? It can discover Drasi queries, read their result sets, and subscribe to change notifications. Now, note that we don't need to tell the agent to do all of that in code. We are simply giving the agent the ability to do this at runtime. The agent can decide when to discover queries and when to subscribe to them whenever it wants. And once a subscription is created, the deltas emitted by Drasi simply flow into the agent's context without polling or plumbing code needed. So let's take a look at a simple hide and seek game where AI agents can be played against human players. Now, here is a hide and seek game where humans can join the game and are shown as a green dot like here. And this green dot can be moved around with the keyboard. And I can also start an AI agent as the seeker. So that will start up as a red dot, and its goal is to find images. Now, the seeker is basically a land graph workload, and the control of this red dot is given to the LLM model. But the model is kept blind. It has no idea where any other players are. Except if we look at the logs here, the first thing that the agent did was to subscribe to Drasi queries. And these queries are the only way it will be able to find a human player's location. Now, let us take a look at the Postgres database in which each player's location is maintained. Now, this is a simple table that we are using here to note the player's positions, and each one is basically just an update on those tables. Now, the agent does not have access to this data directly either, but it does have access to our Drasi query. So let's take a look at that. Well, this is the first query that identifies idle players. And the query is finding all the human players that have not moved for 3 seconds or more. So we are using the true later function here, which is just evaluating a Boolean expression at a specified later time. So whenever a player moves, it will schedule a check 3 seconds later to see if the player was still moving or not. And if not, the player will simply be added to the query result. So note that query here does not need you to write custom code, state machines, or polling logic. It is a simple graph query with some temporal functions. And the second query here is going to help us identify the players that move really fast on the board. Now, this one also is filtering on human players, but only the ones that are making moves less than a second apart. And this, again, is a simple Cypher query, which should be familiar if you have dealt with graph databases. So no polling or state machines, just regular Cypher syntax. Now, if I go back to the game board and I move the player and then wait for 3 seconds, my position then gets revealed to the seeker agent because the player is detected by the inactive player query. And the Drasi MCP server was sending a notification to the agent, and that's how the seeker was able to find and terminate our player. So let us do a quick live debugging of the queries to see how human player movements impact their results. So I'm using the Drasi's VS Code extension here to view the query result sets live, and I will also open a browser tab on the right. So we can add a new player and see how this all flows together. All right. So we have a new player, Joe, join the game. And after 3 seconds of inactivity, we should be able to see Joe appear in the inactive players list. There we have it. And if I move the player Joe, Joe gets removed from the inactive players list. As soon as I made a move on the board, Joe gets removed. And if I wait for 3 seconds again, Joe gets added back again. And if I try to move the player really fast, just by pressing the key, we see that the player was removed from the inactive list and moved over to the fast players list. And these are the changes that are basically sending MCP notifications to the agent. And that's how the agent is able to know the player's locations. Let me quickly also show how I connected Drasi to Postgres. All it took was this simple YAML file, which is just standard YAML with some basic connection details. And I can just deploy this directly from the editor using the VS Code extension. And finally, this is the reaction YAML that configures the Drasi MCP server. Now here we can specify which queries should be exposed to the MCP client or the LangGraph agent, and what description should be given to the agent so that it can then identify or subscribe to whatever queries it needs. And we can also control what kind of delta notifications will be emitted by Drasi here, along with the query results. So that was like a fun little game that we had built, but why should you care, right? That's just a toy, right? But then if you think about when did we notify the agent, right? So we notified the agent when the player was not moving, right? When there was a period of inactivity. Well, that is basically the same as the worst scenario. So you'd basically be building a LangGraph agent which acts as a warehouse agent, right? Which could be notifying the ops team whenever an order is not moving within 15 minutes. The seeker agent also acted when the player was moving too fast. And that's the same shape as the fast transaction scenario. An agent could be notified when tag changes occur within a span of a second, and it can launch an escalation workflow. So with Drasi, you could be building agents that react to data changes across multiple sources, no migration needed, no custom code, just write queries, and the data gets pushed straight to your agent. Here, I was just using Postgres as one data source, but you could also have multiple data sources. All of those could be referenced in a single query. Now, your agent basically can stay in sync with the world, acting the moment a condition is met, instead of checking for changes over and over again and polling all these data sources repeatedly. One last thing is that these notifications are sent to the agent over just standard MCP. And full honesty, so today we still use a small extension of the MCP protocol to carry the payload because MCP notifications are lightweight. But that is exactly why I'm working closely with the MCP working group, which is now standardizing the event streams inside the protocol. But anyways, this is just MCP, so that means we are not just limited to LangChain, right? We could also use Microsoft Agent Framework or Dapper Agents, which is another open source project within CNCF. So as long as your agents are speaking MCP, you could be using Drasi to watch your data changes inside your data sources, and then push these changes to your agents as and when they happen. So that's all I had. The website, the repo, Discord, YouTube, everything is up here. Please reach out if you're building agents that react to data changes, and we are happy to collaborate. I can take any questions if you guys have. Sure, yeah, we have like I think we have a workbook. So we do connect basically any kind of database, API, anything that is climate change, please go. So in that use, so LangGraph is basically an evolution of LangChain, right? So yeah, it's like a workflow based. It's all built on LangGraph. Yeah. The seeker agent particularly, that is able to find. Yeah, let me just go back to the. Yeah, so what's happening is, let me just go back a little bit. Right. So let me just please scroll back a little bit. So if we look at this diagram here, right? So Drasi sources are connected to existing very gaps between connecting to external systems. Now, in this particular case, the Drasi reaction is effectively an MCP server. So you could have even, let's say, your cloud that is running on your desktop connect to this MCP server. Now, in the LangChain example, or in the game example, what's happening is the LangGraph workflow. So like lists MCP servers available to it, then the model figures out, hey, I'm a seeker and I need to find human players. How do I find? But I'm not given any data about their location, right? But I do know that there is an MCP tool or MCP subscription available here, which I can subscribe to. Yeah. So in the beginning of the demo, if you remember the logs show, right? So it's subscribing to this query so that it can then keep on getting those notifications. So to see what's happening within the MCP because getting the data is doing something, it is publishing the information to the data. Yeah. So this entire game and the entire our entire code is on GitHub. So yeah, feel free to check it out. And yeah, if you have more questions, reach out on Discord. We can of course be happy to collaborate. Is the agent going to be falling on the agent? No, not at all. So the agent basically creates a subscription on MCP, and then MCP notifications are sent. So the MCP is like the resource change notifications, right? Okay. So just like an MCP, you have tools, resources, jobs. So on resources, you can subscribe to notifications, and then notifications come in. And then the MCP is sending it the notifications or something else. Exactly. The MCP server is sending notifications to the MCP client, and I'm also working with the MCP working group right now, and very soon there will be like a new events at the top level. and that'll probably be like the protocol moves a bit slower, so we are moving a bit faster. So
Awesome.
thank you. I guess.
It's fair.